Welcome to the Taos seminar today. So today's seminar speaker is Kyungpook, a PhD candidate in atmospheric sciences, Kyungpook National University, Republic of Korea. This is the same university of Professor Gyo Lee, who gave the very interesting talk last week. So, but she is actually working on working with the Professor Kyung-san Lim, Kyo-san Lim, who is a developer of WDM6, which is one of the most commonly used microphysics schemes in the world model. She is working on the modeling realistic ice microphysics and improving the WDM microphysics schemes. So she now visited Stony Brook University to incorporate her microphysics scheme into the Stony Brook University radar simulator CRC. Now she stays here until the end of February, so you can talk with her anytime. So today, she's talking about her new microphysics. Okay, take it away.
Thank you, Mariko. Hello, everyone. Thank you join today. My name is Kyungpook from Kyungpook National University in South Korea. I am currently working at the same place last week's speaker, Professor Gyu-won. I am a PhD student under the supervision of Professor Kyo-sun Lim, not Professor Gyu-won. Today I'm excited to share my research to everyone, which focused on cloud microphysics scheme. Primarily, I will talk about the basic of a numerical weather prediction model and ice-phase microphysical processes in bulk microphysics scheme. Here is a brief overview. I will start with the basic of NWP model to understand of topic. Weather impacts our daily lives in many ways. Everyone here must be quite interested in weather science since this is SoMAS seminar. To predict the weather, we divided the Earth into grid system, use powerful computer to perform massive calculation. This image shows an example of Earth grid system. Also, the below image presents various type of model differ in grid size and model domain size. The model I will discussing in detailing today is NWP models here. The NWP model has two main parts, the dynamic parts and the physics part. It is known that the dynamics part account for 80% of total computations, while the physics part contributes around 20%. In the left figure, you can see the dynamic part is based on 7 governing equations. In the right figure, represent the physics part, which play a crucial role in the model, even though it accounts only for 20%. The physics part focuses on various physics interactions, specifically those interaction between land, atmosphere, and ocean. It handles for processes and motions that cannot be interpreted reserved on the model grid, such as turbulence, solar radiation, cloud formation, precipitation, and wind. These variables interactions are divided into different parameterization schemes, which can be categorized into 5 major types: microphysics, cumulus, radiation, surface, and PBL. Each this parameterization interacted with the others. For example, cloud amount calculated in microphysics influence the radiation, and precipitation amounts from microphysics is passed to surface. Although both cumulus and microphysics scheme deal with cloud, they have distinct difference as shown in figure on the right. When cloud exists within a grid cell, A represents the use of cumulus scheme, while B presents the use of microphysics scheme. To clarify, the cumulus scheme A is mainly used in global climate model with a coarse resolution around 100 kilometers. On the other hand, B microphysics scheme is used the NWP model or cloud resolving model, which have a fine resolution less than 10 kilometers. The boundary between these two parameterization, commonly used as a gray zone, remain an active topic of research. However, one thing is certain: computing power is increases and high resolution model advanced. The role of microphysics is becoming increasingly important. I'd like to more detail of my cloud microphysics. If you can understand this part, you can say that you have almost mastered the cloud microphysics scheme. In microphysics parameterizations, atmospheric hydrometeors classified into specific types, such as a cloud, rain as a liquid phase, and ice, snow, graupel, and hail as an ice phase. Each type has own distinct property. One of the important property is size distribution. Size distribution is generally classified by two types. The spectral bin type, left one, which calculate each size category individually. A Brook type use a functional distribution. Due to its efficiency, computational efficiency, most operational weather and climate model prefer the Brook type, while the bin type is used detailed research for more precise microphysical analysis. In addition to size distribution, other key parameters include the pore velocity diameter relationship, the mass diameter relationship, and density. A microphysical scheme vary their approach to handle these four characteristics, impacting the accuracy and efficiency of weather simulations. Focusing on the Brook microphysics. Brook microphysics scheme can be divided into three types based on predicted variables Q, mixing ratio, and number concentration, and mu, shape parameter. These variables have directly impacted on the size distribution. If only Q is predicted, it is called a single moment scheme. The simplest and most traditional approach. Also, if both mixing ratio and number concentration is predicted, it is called a double moment scheme, providing more detail but require more double moment scheme, which is a common use. The Morrison scheme and Thomson scheme belong to this category. When all three or three variables are predicted is called a triple moment scheme, providing more detail but requiring higher computational resource. However, increasing the number of predicted variables does not always improve forecast performance. And also computational efficiency must also be considered. On the table on the right represent the officially available Brook microphysics scheme in the WOP model. A wide range of microphysics scheme are available from the Kessler scheme of 1969 to NTU scheme of 2020. Okay, now we look at the history of Brook microphysics scheme and two main directions in their development. The first direction focusing on increasing the number of ice phase category to better represent ice phase hydrometers. For example, the WSM series initially started with just two categories, ice and snow, but later expanded to four categories, adding graupel and hail. Similarly, the Goddard scheme incorporated the hail in 2014, and Seifert-Beheng scheme made a similar improvement in 2008. Okay, the second development direction take a more advanced approach by incorporating additional ice phase characteristics. For example, the P3 scheme introduced a factor such as a limed mass fraction and limed density. Also, SoMAS scheme considered the aspect ratio of ice particle. More recently, the NTU scheme has adopted a multi-moment approach to calculate both the shape and density of ice particles. This advanced aim to providing a more detailed and realistic representation of different ice type within the predefined category of Brook microphysics scheme. In line with the current trend in microphysics scheme, microphysics parameterization, my research has been primarily focused on development of WDM series. In study by Lim and Hong, 2010, my advisor, the introduction of number concentration for liquid phase, CCN, cloud, and rain. The WDM series is not only used operational in Korea, also active, but also is active study as one of the Brook microphysics scheme in the WOP model. However, a key challenge with the WSM and WDM series is that the cloud ice mixing ratio is prescribed depending on the temperature, considering low size distribution. As a result, the cloud ice number concentration is diagnosed directly from the mixing ratio, as shown in the figure. X-axis is represent the cloud ice mixing ratio, and y-axis represent the number concentration. This approach may limit the scheme ability to accurately represent ice phase processes. This limitation has ultimately led to excessive surface precipitation, especially in winter season. A study by Lim et al. 2020 mentioned that the WDM6 tend to produce more surface precipitation compared to the other microphysics scheme. As shown in figure, specifically ice, snow, graupel are noticeably higher in WDM6 compared to Thomson scheme. This suggests that the way ice processes are handled in WDM6 contribute to increases precipitation amount. To overcome these limitations, we have developed an enhanced version of WDM6 scheme that incorporates the size distribution of cloud ice. As a result, this new scheme, which I will refer to as WDM6NI, has capability to predict cloud ice number concentration. With this improvement, WDM6NI applies size distribution or hydrometers category. Furthermore, it was the first to introduce the number concentration specifically for ice space. As cloud ice number concentration became predictably, we incorporate more detailed representation of nucleation and Haller-Morse processes. Currently, these processes are represented using the simple temperature-dependent equations, but they can be further improved. Through the experiment on winter season, we can confirm that incorporating cloud ice size distribution to present the key point of the result in both case 1, case 2, the simulation showed a clearly decrease in cloud ice mixing ratio as shown by the red arrow in the figure. Also, the key enhancement can be seen in the figure on the right. The original WDM6 scheme with black line, cloud ice number concentration is unrealistic higher at the low level. This happened because NI directly depended on the mixing ratio, leading to excessive amount near the surface. However, with the WDM6 NI scheme with a blue line, the prediction of NI was show a more realistic distribution with a cloud ice number concentration shifting to higher level. Additionally, the issue of excessive surface precipitation in the original WDM6 scheme has been significantly improved. As shown in the contour plot, both case 1 and case 2 indicate that the original WDM6 tend to overestimate precipitation compared to AWS observation, especially in the mountain regions shown by black box. However, is a shaded area in the figure, the new scheme effectively reduced this overestimate, leading to more accurate precipitation pattern. We have verified this relationship through the detailed budget analysis microphysical processes, although the specific details are not covered in these presentations. These findings suggest that the WDM6NI scheme improved the particle distribution of cloud ice and contribute more realistic surface precipitation. Okay, let me emphasize the important issue that affect both PIN and Brook microphysics scheme, one that continue to be major focus on ongoing research. As mentioned earlier, microphysics scheme classified atmospheric hydrometers into specific type and assign fixed value to key variables based on this classification. For example, density values are typically set to 100 for snow, and cloud ice and graph pair has 500 and 900 and Hale. However, relying on fixed value lead to unrealistic transition between category and pair to represent intermediate type. The figure on the below shows the differences in the radar reflectivity between the Morrison and Milbrandt-Yau scheme depending on whether cloud and hail categories are included. Microphysics scheme depend on hydrometeor classification, making them highly sensitive to how ice is partitioned among predefined categories. So Milbrandt and Morrison 2013 suggested the solution method by adding new prognostic variable called the Graph-Pair volume mixing ratio, shown the BG. This approach allowed the model to represent different density from aggregate to highly dense particles and can capture intermediate type. P3 scheme is well known, the bulk microphysics scheme that uses this method. It's currently used in operational model in Canada. Instead of dividing ice phase category into separated category, this approach determines their type based on predicted property. Okay, our research team aimed to apply this method within a transitional two-moment scheme while preserving the fundamental structure of a double moment scheme. Through the collaboration with Dr. Milbrandt, the developer of P3 scheme, we have further enhanced the WDM6NI scheme as shown in the figure photo. Dr. Milbrandt and my advisor, and here I am. We have several meetings to discuss our progress and future plan. As a result of this effort, we developed an advanced version of WDM6NI scheme called WDM6NI-PG or KDM, which includes the capability to predict the graph density. This approach is significant because while it retained the conventional hydrometeors category, it allows for more detailed representation of graph pair by using its density. And also, furthermore, the WDM6NI-PG scheme has been adopted for operational use in Korea regional weather model. And also, we have officially proposed its implementation in the WAP model. Okay, to briefly explain the method in WDM6NI-PG, the graph volume mixing ratio is calculated using this equation shown. In this equation, retailed microphysical properties such as accretion, melting, and evaporations are considered in microphysics module. Graph density is predicted by calculating the ratio, the graph mass mixing ratio to a volume mixing ratio as red box. As the graph density changes, the parameters in core velocity diameter relationship and mass diameter relationship can also adjust accordingly. So the varying parameters are summarized in the table. The figure on the left shows the VD relationship, bore velocity and diameter relationship with red line represent WDM6NI and black lines representing the WDM6NI-PG. from low to high, and also as shown in the cross section on the right, the simple to the idealized scoreline experiment, our approach effectively captured the changing in graupel density the storm develops. It is important to note that the WDM6NI scheme graupel density is fixed at 500, whereas the new scheme allows for more dynamic representation. To evaluate the performance in real precipitation event, we conducted winter case study over the Korean Peninsula. For comparison with observed graupel particle, we used from instruments such as 2D and mask data, which provide a valuable insight into particle characteristic. Most of the observational data handling was done by Dr. Gon. Big thanks to him. This figure presents a key result from the simulations, highlighting the impact of density predictions in WDM6NI PG scheme. This figure shows the rho V relationship at the MHS size for case 2. The x-axis is shown the graupel density, and y-axis is the pore velocity. Curves are normalized frequency of pore density. In the WDM6NI scheme, a fixed density value is used, resulting in a very low pore velocity that depending on the mixing ratio and number concentration. In contrast, the WDM6NI PG scheme provide a more realistic representation by simulating a low V relationship that closely align with the observations. Compared to WDM6NI, the improvements achieved with WDM6NI BG are remarkably clear and significant. Although some difference between the simulated and observation graupel density, these discrepancies can be further improved through the future refinement. These results confirm the significant role of graupel density prediction in enhancing model performance. Let's move on the ICM 2024 result. To further support our finding, we aim to evaluate them using limed ice particle observation. Fortunately, we have opportunity to participate in ICMW 2024, a workshop that provides a platform for the cloud modeling community to discuss current challenging and advancement. ICMW 2024 included 5 case studies focused on recently model innovations. The case I contribute as a co-researcher, case E, focused on winter orographic precipitations event observed during the Ice Pop 2018 field campaign over the Korea Peninsula. This case, abundant moisture from East Sea was supplied to Taebaek Mountain by northeasterly wind. The Ice Pop field campaign provides a high quality observations, offering a valuable opportunity to compare model results and evaluate their performance. Professor Gyuwon and Dr. Kwon take care of observational data, which was a huge help for this analysis. In this photo, you can see the workshop participant. The main goal is of this case is to answer the questions. What is the sensitivity of microphysical property on representation of rime ice in microphysical scheme. The experiment focused on cases where both deep and shallow system coexist. Many researchers focus on cases where many researchers participate by using different model and Brook microphysics scheme, as shown below. A P3 scheme from GEM model, and WDM series in the Waffle model, and Seipert Behang from ICON model, and DESCOM from model of Klahak. In particular, the P3 and WDM6 and IPG are notable because they can predict global density. The other schemes are double moment scheme with fixed global density. Given our limited time, I will focus on result analysis result for MHS site only. First, let's look at the surface precipitation. We noticed some differences between precipitation measured by AWS rain gauge and precipitation driven from multi-radar. We also compared the precipitation simulated by model with multi-radar observation. The result shows the WDM series in the Waffle model and the Seipert Behang from ICON model overestimate precipitation amounts. In contrast, the P3 scheme provides a more reasonable precipitation pattern, showing better agreement with the observation. Next, we analyzed the radar reflectivity result using data from X-band radar. Since we are already aware of limitation in how models simulate the radar reflectivity, our analysis mainly focused on identifying overall trend rather than exact value. All models are able to capture the timing of the system development quite well. However, they generally overestimate the reflectivity, indicating a tendency to simulate stronger precipitation signal than observed. In addition, the reflectivity pattern produced by all models were quite similar, and no significant differences were detected among them. This suggests that the model provides similar simulation of the events. The precipitation measured at MHS site using Fluvio showed two peaks, which compared to the deep and shallow system. The model captured the first peak well, but they were different in how they simulated the second peak. The P3 scheme, blue line, and ICON, Seipert and Behang, green line, scheme successfully captured the second peak, while the Seipert Behang scheme tended to overestimate it even more than first peak. This image shows a time series of the rime index from mask data, along with an image on ice particles. The rhyming index displayed two distinct peaks, and these times yellow shaded. The image reveals the more rounded and limed ice particle. WDM6 and IBG, blue line, and P3 scheme in the below bottom figure successfully captured this peak. Their ability to predict the global density allowed the better simulation of liming processes compared to the other scheme. This result highlight the positive impact of global density prediction in Brook microphysics scheme for improving the representation of rimed ice. We are currently working with co-researchers to finalize our finding and prepare joint publications. Finally, I'd like to wrap up by sharing some additional research effort that currently in progress. Most ongoing researches are focusing on comparing and analyzing various microphysics scheme across the different spatial and temperature scale. This effort aims to improve our understanding how different scheme simulated cloud and precipitation processes under the various atmospheric conditions. However, making direction comparison between schemes is quite challenging. This is because each scheme uses different microphysical processes and internal structure which can be lead variation in the model result. For this region, it can be difficult to pinpoint the exactly cause and effect of these differences, requiring careful analysis and interpretation. Even though these challenges, continuing this research is crucial to refine and improving model microphysics scheme. So we aim to gain deeper understanding of ice, of how adding prognostic variables and introducing new category impact model performance. As part of this effort, we have developed the WDM7NI, which included the hair category. By systematically comparing these three WDM series, WDM6NI, WDM6NIPG, and WDM7, we can better understand the effect of these new parameterization method. This comparison help us better understand how the introduce of numerical model, new parameterization method for the ice category improves the model. How can we identify, how can we effectively compare the result of different microphysics scheme? How can we verify the microphysical simulated by the model? I believe this important question that we can discuss together. Even if a simulated precipitation amount and distribution close match observation, but we cannot say that the microphysical processes in the atmosphere are realistically representations. Traditional methods often focus on comparing surface precipitations with observation. However, this approach has limitation because it only reflected a binary outcome of numerous microphysical processes. Building on these challenges, I'm here to learn more about CRSIM and how it can be applied to enhance the verified of microphysics scheme. CRSIM is advanced radar simulator, can generate a variety radar variable from model outputs, making it excellent to compare microphysics scheme in greater detail. Collectively, the module participants in ICMW 2024 have already been incorporated, and with incorporating the WDM series during this visit, the research could be further expanded. I'm truly excited about this opportunity and look forward to applying CRSIM to advance my research. Yeah, thank you for everyone. I'm truly appreciate the opportunity to share my research with everyone. I welcome any questions, feedback, or discussion. But since English is not my first language, I'm not fully understand your question right away. But yeah, I appreciate your patience and understanding. Yeah, thank you so much.
Thank you, Sarnion, for great talk. Do you have any questions from students or postdocs? All right. Questions?
Yeah, thanks for this talk. I may have missed something. You showed the case study of North Korean with the deep convection and then the shadow. You compared the different models. The P3 scheme seems to have done a bit better than your scheme, your new scheme. But I thought your scheme is built partially on the P3 scheme, or there are some similarities. And in the shadow convection, the P3 scheme got the halo crowd, but not your scheme. I was wondering, in your opinion, what is the major difference? Is it a better parameterization of the crowd density or volume, the P3, or I did not understand why they differed so much, the results.
Yeah, that's an interesting question. I think maybe I did say that the basic fundamental structure is different between P3 and WDM6 and IPG. Yeah.
Yeah, I'm not an expert in that, so please explain.
Yeah. P3 scheme is no separate the IC category. WDM6 and IPG preserve their pre-category. P3 scheme just only predicted variable using calculation microphysical processes, just only a storm cell structure. They have for example, in shallow region, using the predicted variable, just we can just consume that it must be rain or cloud particle in core region. Rime dense and volume is bigger. We can only diagnose the type is hail particles. About the WDM6 and IPG, they show output variables in pretty defined categories. So that is.
I thought, so I misunderstood. I thought also in your scheme you varied the density like in the P3 scheme, but you did not. You still have the category.
Yeah,
okay,
they remain the yes. So.
Okay. Thank you.
I have a related question. The last two figures, last slide, not the last one, second or third from last, no, that one, before additional works. Like you compared the particle density, actually line fraction from observation and models. I missed it. What was the best matching? What is a good representation with the observation? What model is good for compared with observation?
Do you mean the what variables?
What means what density? What model should represent the density of particles, density of the globals, compared with observation? You showed some safer than model shows very big line mass fraction.
Yes.
But some cases are very small mass fraction. What is a good?
Yeah, you can say that this figure.
Yeah, this figure.
Actually, this slide calculate the Q graph pair, the ratio of Q graph pair and some of ice, snow, and graupel. Maybe the P3 scheme and WDM6VG scheme produce the less graupel mixing ratio. But I need more a moment. I will check that and get back later to you. So sorry. Wait, next meeting.
Yeah, we can talk.
Yeah.
Any other questions? Oh, yeah.
Just want to follow up on Daniel's, and I'm still confused a little bit. If you have a variable density for grapple, then I'm just curious, why do you still have these categories? And then furthermore, what does snow represent in this approach? If rhyming represents grapple, slight rhyming to heavy rhyming, is the snow category in your scheme just pure, dry, unrhymed snow, zero rhyming? I guess I don't partition between snow and grapple. If you're maintaining that partition, I'm not sure how that fits in the context of variable density.
Yeah. Actually, we focus on the this approach just to show similar snow or similar hail. We use the bound. We use the range of graupel using graupel. Sorry, I don't. Yeah.
So snow is lumped into grapple now. So there is no. I guess yeah. What is the snow category?
Snow
The
is
density of snow is that
100.
okay? So that's constant. So you have a constant snow density.
Yeah.
Which is unrhymed.
Yeah. Online the
and
particles.
everything else is thrown into the grapple from slightly rhymed.
Yeah. Sorry. Yeah.
Any other questions?
Just an observation, since we're on the slide. The left one is observations.
Yeah.
I've never seen a graph with observations that are so close to each other and so continuous over this large range. I'm astonished.
Yeah. Thank you. This slide shows the result only MHS site 1 point. So maybe this observational data handling with Dr. Khan. So yeah.
I don't even know how fall velocity. I know how you can measure that. You have instrument that can measure the speed. That's easy. But density, I think, is very hard to measure. I don't know how you do it, and I just kind of, in some sense, I looked at this figure and I said, "Whoa, it's amazing."
Yeah. Thank you. Yeah. Thank you for your comment.
I have
Yeah.
a question. Global, the x-axis is global density and y-axis is the force speed.
Yeah.
I think force speed also partly depend on the size. But
Yeah.
you have only one line, one global density and one velocity. How did you get it?
Because the first model cannot represent the actual particle size. We just only calculate the mass weighted diameter, or just only using the Q and N can produce the diameter. So we choose the comparison variable graupel density and bore velocity, but diameter is not considered this analysis.
But observation has also diameter.
Yeah.
How did you remove the effect of diameter in this plot?
Yeah, just plot. Yeah, just the row and just the bore velocity used.
I think I misunderstand or
Oh,
I didn't follow.
Sorry.
The observation measure the global density. Okay, maybe you have some equation. And then also this has a size. The velocity also depend on the size and also depend on the density. I thought that the velocity and more distributed at a given density. But this showed observation. The observation showed only one value at a given global density. I don't know why.
Oh.
Is Crowell density a mixing ratio? It's just more Crowell per cubic meter of air. So the probability that you have larger Crowell with higher fall density goes up. But then you look at the density, and there are only a few large ones which have that larger velocity. It's almost like a probability density function. Therefore, it looks so smooth. So I think it's not the density of a single Crowell. It's just you have more Crowell per cubic meter air, so you have the likelihood of larger Crowell which has higher fall velocity, but only a few. Therefore, it's blue, and the center is somewhere in the middle, or the highest frequency of the density is somewhere in the middle. So it's like an S-shaped curve related function.
Yes, thank you.
So
Thank you.
therefore, it's not scattering. So if you would have the individual bins measured, it would look scattered, but line. Foundation folks can help me out. Anyway, okay.
Yeah.
My comment. So it makes sense, but it's a difficult one. It's multi-dimensional.
Any other question? Okay, thank you for
So much.
Thank you.
Thank you so much.